the whole polynomial division, zeros, roots, all that sort of stuff is done. You're going to go back, you're going to refresh every now and again. Last lesson, we started looking at composition of functions. So it was about notation, and quite frankly, you've already been there, done that. All right? The only new thing, like you would have seen this last time, the only new thing is that they're writing it like this now. I call that fog. Okay, so if you see f with a little open dot g, that just means it's f of g of x. And what does that mean? It means whatever g of x is, wherever x is in your f function, replace it with that thing. The bit that we had to remind ourselves about was domain and range. Domain was the values of your x's, range was your y's. Who can remember the things that you had to think of when we're talking about domain? When do things exist and not exist? I'm going to make me use the F word. Undefined. Fractions. So when we have fractions, the denominator cannot be 0. When you say surds, we're talking about?
Negative.
We cannot square root a negative value. There was another function that we know where sometimes things are undefined. Tangent functions, yes, and then the inverse of sine and cosine, arcsine, logarithms. Okay, you cannot log 0 or a negative value. So just think of those when we're talking about domain and range. So just, you don't have to write this down. I will save it if you want to, but it's just a recap of, I want to say 3A, exercise 3A. So if you didn't get to it, it's quite short, sharp, shiny. You go back, you have a look, you're playing around with these sorts of things. And you will find that it's sort of embedded in the inverse functions that we do today. So if we had this, we've got two functions, f of x and g of x. If I had a third function, I could call it, so many options. I could call it a capital F of x. I could call it h of x, all those sorts of things. So please make sure when you are using your notation, little f is different to capital F. All right, so this would be, it could be written like that, and I just go, if I see that, I just go straight to Okay, so that is saying wherever the g of x is, so what is g of x? I pop it there. I don't like to skip steps because I end up making mistakes. This is now saying go to my f function, and wherever x is, replace it with root x plus 4. So on the top line it becomes 4 times not x, but x plus 4. Downstairs it is root x plus 4 plus 3. Agreed? Now, to play around with our domain, we have to think about, okay, when is this defined? And that square root is big old looking me in the eye and going, do something with me. So clearly, at the moment when we're talking about our domain, what has to be the limit on x? -4. So when you say -4, what does that mean? Correct. So it has to be, so x is greater than -4. When you said 5, that's lovely, but we can also have it as like minus 3.9999999. 9 plus 4, that will give me positive 0.0000. God knows how many nines I just said before, but that would still work. Agreed? We've got one other little proviso, and I was just sort of doing this on the spot when I came in, so I'm not actually going to finish it because I now foxed myself a wee bit, but we've got another proviso. What's that? Why can't it be equal to 5?
Because 5 plus 4 is 9, and then under the root is 3. Oh, wait, no.
We've got this little proviso. You're on the money there, right? I should have, so in hindsight, I should have gone, yeah, instead of plus 3 at the bottom, I should have gone take 3. But anyway, we've got x plus 4 plus 3 has to be not equal to 0. So, yes, in my mind, but I was chatting, it should have been a take 3 there, because absolutely you would then say x cannot be equal to 5, because, do you get that? So we're not going to have to finish that too much. Just be aware. To get the range, that's actually, save yourself a little bit of a hassle there, and you can pop this into your calculator and graph it. Okay. We're also going to look at today, hopefully if we get there, a little bit more when we talk about asymptotes with the bottom, and that's what we're talking about. For this, we're looking at the domain and range of our final function. But we will be looking at asymptotes today. Just wanted you to be aware that when you have a quadratic, that's when you have to think about the range, because if you've got your, I don't know what happened then, what's going on? I did not press that. If you've got your vertex as, I don't know, 1 minus 7, how does that affect your range? It can't go lower than minus 7, and again we write that by going y, and it would have to be greater than or equal to minus 7. But you're not going to just get, a quadratic every now and then. You'll get some crazy ones, and you will get your graphics calculator to help you with the domain and range. Does that make sense? All right, so we're talking about inverse functions. Your textbook has a nice sort of definition. I've just summarized it a little bit. Oops. No, I can't make that bigger. My touch board has left me. And straight away it talks about what's a one-to-one function. So if it's a one-to-one function, it will have an inverse. What is all of that on about? Very simple. A one-to-one function has to pass the vertical line test and a horizontal line test. Now, you've heard of the vertical line test before, because that's what makes it a function. What is that? Who can remind us of the vertical line test?
Two values of y for one value.
Right, yep. You get your ruler, you get your whatever, and it can only cut your function once. Okay, so our good old friend, cubic, put any vertical line anywhere around, only cuts it once. For every y value, there's one x value, right? Boom, it's definitely a function. However, if you have a cycle, vertical line cuts it twice. That's no good. Not a function. And then to make it actually one-to-one, it's past the vertical line test, then it has to pass the horizontal line test. So unfortunately, the thing that I just erased, which now I can get back, okay, our cubic is definitely a function, but is it a one-to-one function? No, no. It's not a one-to-one function because it will not pass the horizontal line test. So boom, 1, 2, 3 spots, it cuts it. Okay? You can adjust the domain so that you could make it one-to-one. So if I said, all right, let's go from here to here, that now becomes a one-to-one function just within that. So we can mess around with domains, and again, that's you just reading the notation, okay? And we talked about that, the whole greater than and less than thing, the other lesson. So, has to pass the vertical line test, that's what makes it a function, and then the horizontal makes it the one-to-one function. We happy with that? Let's go back to what is the whole deal with an inverse function. It's on my little page there. You've got your notation, it's f to the minus 1, and it's basically a graph that is reflected, oops, it's reflected in your y equals x axis. So your x values become your y values become your x values. So if I've got that, and I will put that now, I wasn't going to, and now I'm glad I did it. Because I do like to put these as in test questions. Hope everyone had a nice weekend. So let's imagine, I mean, it's got it on here at the moment, but this point here is clearly 2, 0, and this point here is 0, 2. The x and the y's get replaced, and it happens as you go along. So if I've got, let's say this one, let's say that's 4, and maybe that's, I don't know, well, let's say it's, shall we say it's 2? So that point there would be 4, 2. So that means 2, 4 should be on this one, and it looks like it is, doesn't it? So you just flip the x and the y values. And so in order to find the inverse function, that's exactly what we do. Where we see the x, we're going to replace it with a y. Where we see the y, we're going to replace it with an x, rearrange, and that will give us our inverse function, which we denote by that. Where do we use them? Oh, just to mess around with the algebra, okay? Write the example because I think it's very simple. All right. They've given you, they would have already graphed y equals 2x plus 3, and we know, is that the red line or the blue green line?
Green line.
Yes, we should know because intercept, y-intercept plus 3 going positive 2. So all they have done is they've taken a couple of points from here and they have reflected and boom, they've graphed it. Okay. Find the inverse using coordinate geometry. So that would then be you've got those 2 points. Right, how did you get, that's the y-intercept you've got, they just picked. When x is 2, pop it in there, you get 7, and so then you can, how can you get the inverse when you have 2 points? Sorry, how do you get the equation of a straight line when you have 2 points? Slope and a point. You've just been doing that in methods over and over and over again, except this time to get your slope, you're not going to use calculus because it's a straight line. You use your good old slope formula. So they're just making you get the equation of the inverse, and then they're showing you, so it's really drawn out, that the better way, especially when it's not a straight line, if it's a curvy sort of thing, to get your inverse, notice wherever the y is, you replace it with. Wherever the x is, replace with y, and then do a little bit of algebra magic Houdini to get y by itself. That y is then your inverse. So don't get bamboozled with the to the -1 and all the f in the brackets. It's just notation. We okay with that? If you find f of the inverse, you end up with x. If you find the inverse of that function, right, f to the -1 of 2x, you get x, and that's how you know you've done it right. How often will you do that? Give you to have a read of the example 2 if you want to, but the whole point that they're trying to make here is that this is clearly a function, but it is not one-to-one because it cuts twice on the horizontal line, right? So what we were talking about before, you can now turn this into one-to-one by limiting its, domain. And then, oh, huzzah, yep. When you swap the x's and the y's, how do you get rid of a squared? You square root, and that will make sense, I hope, to me and to you. Right? You could probably predict where this might be going. Some of the things might be find out where the inverse and the function intersect. A little bit of algebra there. Again, things like this you've done in methods, part of calculus, just that algebra part. Okay. So, the other thing is when you see this, don't get panicky. You could just rewrite that. You read it and you can just write that as y equals 3x plus 1. Okay, you don't have to use that same notation as long as you can read it properly. Are we good with that? I don't think I really want to do 1 and 2. After the following functions, and I'm doing this quickly because it's very simple and you won't get questions like this, but you never know. So, draw the graphs of y equals x and then y equals, then do the inverse. So we would have a nice, you know, y equals x, 1, 1, 2, 2, 3, 3, so on and so forth. As we talked about already this lesson, we know this coordinate is -2, 0, which means the inverse must have the coordinate, right, 0, -2. Shall I keep it in purple? Why not? 0, -2. And then this coordinate is 0, 5. So then we go 5, 0. They didn't leave us that much room. Let's maybe go here. 5, 0, and basically you make sure that it's a bit of a reflection. Does it look like it's a reflection? Pretty good for not much scale. Been recording then. I was talking into the mic. I don't know.